Hey, good to meet you guys. Thorough YouTube, and so from today I should make a video, because I met a good professor who gave me a good opportunity to make a video, like make a review video, about the class what I learned. Yeah, so that's why I do this. And so last week I learned about band theory, and before I talk about band theory, just imagine that there are one hydrogen atom, and this is free space. So, and maybe you can see this kind of potential energy, but if you have two hydrogen atom and it is start to closing to each other, maybe the potential energy is overlapping. So maybe you can see this kind of potential energy graph. And so um, if you imagine three hydrogen atoms, this is different input when you think about eigenvector and eigenfunction. So it makes different energy potential in here. And so about band theory, you can see conduction band and forbidden band and balance band. The definition of balance band is the highest level, highest energy level, which is fully occupied by electron. And conduction band, the definition of conduction band is the lowest level which is completely empty. So the concept is like this. Just imagine that there are the room and it's very hot, like almost 300 Kelvin degree, and electron can be jump. I don't know the word in English. Uh, so they can make a lot of holes in here, so electron will be flow. So this is the concept of hole, and it's called electron hole pair, like this, something like this. And you can distribute the material, like you can distribute the material using the standard, whether it is can how much is the long, how much they have long forbidden gap. Like look at this, in insulator there are way way they have forbidden gap way bigger than semiconductor, and in metal you can see almost the same conduction band and valence band. So maybe electron can follow more easy than semiconductor and insulator. And also you can distribute the materials using the different standards, like how they arrangement. So you can distribute three. First is crystalline, second is polycrystalline, third is amorphous. Oof. So crystalline is the near perfect periodic arrangement, and polycrystalline is that composed of many microscopic crystals called grains. And amorphous, oh, what is this? It's like non-periodic arrangement. And I also learned EK diagram, and the professor said that the most important thing is that this graph, as you can see in this graph, yeah, maybe it is impossible for you to see this graph. I'm so sorry. But in this graph, anyway, you can see that it is different, like different conduction band edge. I mean that when electron jump from valence band to conduction band, they need more potential energy. Yeah, they need more energy than before. So, and also if they drop from conduction band to valence band, they can emerge some energy. So if you draw EK diagram, you can check um, this energy. So he said that's why we draw EK diagram, something like this. And about donor and acceptor, when you have intrinsic semiconductor, something like this, um, you can see donor and acceptor when you have intrinsic semiconductor and you put some material like called dopant, and if you make some electrons, it is called donor, and if you make some holes, it's called acceptor. And important thing is that there are no charge. I mean that it is only ionized like this. Uh, big, and Fermi level. Fermi level. The definition of Fermi level is the probability, which is the electron exists is 50 point. So upper the Fermi level, maybe the probability is 0, and down to Fermi level the probability is 1. So when you see the Fermi level, you can assume that, oh, this one is n-type semiconductor, or this one is p-type semiconductor because it's close to valence band like this. Yeah, and may have more holes like this. And I also learned the density of states. Density of states is proportional to electron field, and it is different when it has 3 dimension and 2 dimension, second dimension. No, 2 dimension. No, I don't know the word. Anyway. And this is um this is density of states, and this one is Fermi-Dirac distribution. And if you multiply, you can see this kind of graph. And he said that this sentence is very important. So yeah, that's all. I thought that I almost understand what it happens in here, but it is very hard for me to explain in English. So sorry, but this is my first lecture, not lecture, first review video. So next time maybe I will make a way better than this one. And thank you for everything. Bye.